So I'll be quicker this time because the earlier when I took the session offline, I kind of missed recording this. So I'll be a little quicker. So we covered the probability basics with some examples and going back to the history, how it started, how has it evolved, and we ended with the conditional probability. So before in the previous sessions, we covered the statistics basics, including the importance and the applications in real life, how we can present the data, the presentation and the interpretation. This included visual representations as well for the charts in form of charts, graphs, and tables, also the histograms. And then we covered the center and the spread of the data, which basically is the median and the mean. uh, IQR is interquartile range and the standard deviation. We use them for spread of the data measure, and we covered the Z score as well in the previous sessions. Now, moving on to probability. How probability started? So way back, it started when Caesar was the head uh, for the Roman civilization, I guess, or the Greek civilization, I think. So they used to go. They used to bury an astragali, and they wanted to cheat death. So somehow, actually, nobody knows when the gambling began, but this is where people can get its traces to, right? So ancient Egypt, basically, and so the Roman emperor, there was a Roman emperor Claudius, who has written his first book on this treatise of gambling. Okay, and when they used to bury the body with the astragali, they were trying to do a gamble only. Okay. So this book was titled "How to Win at Dice," but this was lost somewhere. Okay. So now let's take an example of a gambler. Let's call him Chevalier or Demier. Okay. This is again someone from the history, but not sure if he was there or not. But anyways, we'll take this example. Okay. Let's consider it. Consider this as an example only. So he used to have do certain shows, and the problem that he got into was what is going to be more likelier. So event one is rolling one die, and what are the chances of getting six in four throws of a single die. Okay, this is event one. The event two is uh, they are rolling a pair of dice, and they are rolling it 24 times. What are the chances of getting at least one double six? Okay, so these were the two events that he was trying to compare. Now let's see what happened after that. So sorry. So Chevalier reasoned that both the events, basically event one and event two, they should have the same probability or the same chances. So any one of them is not likely. Okay, so let's see how he went. So for the event one, the chances of getting 1 6 are 1/6, and they since there are four rolls happening, so the chances of getting any chances of getting six in any of the dice roll out of these four rolls is 4 into 1/6, which will be 2/3. Now the second event in which he's rolling a double die, chances of getting a double six are 1/36, and since the roll is done 24 times, so the chances are 2/3. But what he observed was, since he had a big amount of data or the gambling that he had done, so he said that he observed that he's losing more often with the second gamble, which is the two die rule. So now let's see what he did after that. He approached Blaise Pascal after this with this problem. Blaise Pascal was a mathematician who was popular at that time. He later on developed a theory of probability. Let's see how he went ahead with this. So he was too bored actually at that point, but when he got interested in this problem somehow, and he wanted to see why it is happening. So they put forward the theory of probability, which we know in the present form. Okay. So that is the history of the probability that we know. Now let's cover some basic definitions starting from a random experiment, right? So a random experiment is nothing but the process of observing the outcome of any event, of any chance event, is a random experiment. Throwing a die or tossing a coin is a random experiment. Second term is elementary outcomes. Elementary outcomes are all the possible results of the random experiment, right? So let's say if we toss a coin, then the elementary outcome would be head or tail. So elementary outcome would be head, one would be head, and other would be tail. Sample space is just a collection of all the elementary outcomes. Okay. So whatever can be the results of my random experiment are there in the sample space. Is what we can say. So let's think of not rolling a die. Let's think of tossing a coin. Okay. So the random experiment is recording the outcome. That is the random experiment. The elementary outcomes are heads and tails, and the sample space is basically a combination or a set having all the elementary outcomes, which is heads and tails. So this is how we represent the set. Now, if let's say this experiment was a dice throw. Okay, so a dice is popularly used in India. We play Ludo from it, right? So the elementary outcomes are 1, 2, 3, 4, 5, 6, and again, if we extend further, if we roll a pair of dice, there will be 36 elementary outcomes. Okay. We can let's say we roll a white die and a white dice and a black dice. So these are all the elementary outcomes. 36 basically. Extending it further, if we roll three dice together, the the space would be 216, which is 6 cross 6 cross 6, right? So the sample space we can say here is going to exponentially increase with number of dice or multiplicatively increase, I would say. Now, enough of these manual things. Let's go on to some real representations in mathematics. Let's imagine a random experiment with outcomes of 1 up till ON, and we want to assign a numerical probability to every one of them. So, how we represent it, how we write it is the probability of OI. We write it as P of OI, where OI is the event. It can be O1, O2, or up till ON. Now, in the example where we are tossing a fair coin, this term is important here. Fair coin. So the probabilities of getting heads and tails are equally likely because it's a fair coin, and the probability would be 0.5, okay, for both of them. Now, when we are rolling two dice at once, there will be 36 elementary outcomes as we saw earlier, and all of them will be equally likely. So the probability of each is 1 by 36. For example, if I say what is the probability of getting 5 on the first die, black die, and 2 on a white die, that will be again 1 by 36 because 5 and 2 is one of my elementary outcome, right? Now, what it means, okay, what probability actually means. So, if I was to roll the pair of dice and a large number of times, let's say 1,000 times or 1 lakh times, let's pick up 3,600 times. If we rolled it 3,600 times, then this outcome, black 5 and white 2, would come exactly 1/36 of the time. So if we are rolling 3,600 times, then it would come in 100 times. 100 times we would see black 5 and white 2. So that is what we actually mean by probability. Also, if we want to test the equal likeliness of all the outcomes, we can do this. If we want to see certain dice is biased or certain coin is biased, we can uh, perform the random experiment large number of times, let's say 1,000 times or 10,000 times, and then we can see if the probability or if the occurrences of both the um, events or both the sample space, um, all the members of my sample space, are they equal? If they are equal, then it will be a random. It will be equally likely thing. Moving on. So now let's consider a dice example where it is biased. Biased meaning the chances of getting one number are higher compared to the other numbers. Let's say in this example, uh, somehow the magician or the person, Demir, he has biased the die, and the chances of getting a one is 25% or 0.25. The probability is 0.25. So then now the chances of getting a one is 0.25, but the chances of getting all the others are equally likely. So what we do is how we can identify the probabilities of every other outcome is basically we will subtract 0.25 from 1 because the sum of all these probabilities should be 1. And then once we subtract it from 1, we can just divide it by 5, the remaining outcomes, because they are equally likely. Right? So we get a probability of 0.5, 0.15 for all the five numbers basically. Moreover, in general, elementary outcomes, all the elementary outcomes, they do not have an equal probability. Right. So here we see an example where the weather forecast says the probability of precipitation is 20%, and the dog thinks if the probability of precipitation is 20%, the probability of me going for a walk with the owner is 5%. This brings on to a corollary, I would say, that the probability of any event is greater than or equal to zero. It cannot be negative because zero probability doesn't mean anything. Zero. What does zero probability mean? Zero probability would mean there are no chances of getting that outcome. Basically, that elementary outcome is not a part of the uh, sample space. So, for example, if I roll a dice and I say what is the probability of getting a number 7, so that would be zero because 7 is not there on the dice. Right. Moreover, extending this, we can say that for a sure shot event, the probability is always 1. So if we say that in a roll of dice, what is the probability of getting a number lesser than 7? So it will be 1 because all the numbers are lesser than 7. This again brings me to one more corollary. The probabilities are non-negative. This we already discussed. Non-negative. They may be equal to 0, but they are non-negative. Also, the probabilities of all the sum of the probabilities of all the elementary outcomes is 1. Like now, this guy has lost his shirt, so there are problems in his life now. He'll be looking for a shirt and coming slides as well. Now, since statisticians are more systematic, so they don't want to skip the basic questions. What does the probability mean? How do we assign probabilities to outcomes? Blah blah. He's trying to find similarities with politicians or do a comparison with politicians because politicians who skip some of these kind of questions, basic ones. So now let's discuss some of the approaches that have been taken up till now. Classical probability is the one that we had discussed earlier, where the Chevalier Demier was comparing two events and seeing okay the likelihood of both of them occurring is the same. That is classical probability. So the classical probability assumes that the elementary outcomes have the same probability, which means the probability of getting 1, 2, 3, 4, 5, 6 when one dice is rolled is the same, right? So that is classical probability. One more term that we cover here is the relative frequency. Relative frequency, what does it mean? Is when we repeat an experiment, what is the probability? The event probability is going to be the proportion of the times that event has occurred in the long run. Let's say if you are doing uh, if you're rolling a coin or tossing a coin or rolling a dice 1,000 times, then how many times it occurs? The proportion of it is the probability, event probability. The next thing is personal probability. So most of the life events are not repeatable. I would say most of the things that we drive in our personal lives are based on our personal probability. So it's actually our assessment of the outcome. Okay, what we have seen from the previous data that we have learned or from the previous learnings, right? So now we kind of divide. So scientists have always seen this division, right, between a person who believes by doing actually empirically, and the one person who goes by the theory. We call him Bayesian, who goes by the theory, and objectivist is someone who would want to see the experiment first before commenting on it, right? So objectivist uses either classical or frequency definition of probability, whereas Bayesian or a subjectivist, they apply formal laws of chance to their personal probabilities. Okay. So yeah. Moving on, we'll come on to the basic operations, okay, and we will define what is an event. Event is a set of the elementary outcomes. Okay, let's say we have an event where we are doing a random experiment where we are rolling two dice at once. Now there can be different events that depends on the user defining the event. Um, so the elementary outcomes of uh, event A, event A is the numbers of dice 3. The elementary outcomes for this event 1, 2, and 2, 1. Okay, and the probability of event is the probability of these elementary outcomes, which is 1 by 36, 1 by 36. So the probability of event A is 2 by 36. Again, I would like to reiterate, we could have derived this all very well with some common logics, but we want to align with the theory of probability as well and the representations also, right? So similarly for event B, dice adds up to 6. The probability will be 5 by 6. These will be the all the elementary outcomes, and so on and so forth for C and D event. Now, what is the beauty of using events rather than elementary outcomes? One thing is that we can apply a certain logic to them. So basically, we have and or not logics, which are kind of standard. So what we mean when we say E and F, E and F means that event E and event F are both occurring at the same time. E or F would mean event E or event F occurs, and not E would mean event E does not occur. We'll see examples for that. Now let's consider the scenario where we are throwing two dice at once. Okay. So in this example, my sample space is going to be all these elementary outcomes, 36 outcomes. So uh, C, the event C is getting a 1 on a white die, and event D is getting a 1 on a black die. Okay. So this area here is the event C. Okay, and event D is the sixth column, basically this one. Now C or D. When we say C or D, C or D meaning either event C occurs or event D occurs. So that's yeah. So let me just highlight event C. So this is event C, and this is event D. Okay. Yeah. So C or D means either this or this occurs, and so C or D basically means there is one there is one on either of the die. Okay. And C and D is there, both of them are one. So this is just this one. Now let's see how we have the technical representations or the standard representations of this. We say that the probability of E or F is equal to probability of E plus probability of F minus probability of E and F. This is the standard equation. Okay. Later on, we'll substitute it with the standard symbols, but for now, we'll use or and. So in this example, the probability of C or D is going to be 11 by 36. How 11 by 36? The probability of C is 6 by 36. Probability of D is 6 by 36 again. Now probability of C or D will be equal to probability of C plus probability of D minus probability of C and D, which is again probability of C is 6 by 36, D is 6 by 36, and C and D is 1 by 36. It means 11 by 36. Probability of C or D is 11 by 36. Similarly, let's talk of two other events, A and B, where they are mutually exclusive. So this is an important term which you will see very frequently being used when you are trying to identify the probabilities. Mutually exclusive events would mean there is no common thing in between them. So let's say event A, in this example, again, two dice roll. And in this example, event A is a sum of 3 occurs on both of them, or a sum of 6 occurs on both of them, right? So we see here that these will be mutually exclusive events, and in that case, probability of E and F will be 0 because they are mutually exclusive. That's why their probability of both of them occurring is 0. So in that case, the equation modifies to probability of E or F is equal to probability of E plus probability of F. Also, we can check that here that probability of A or B will be 7 by 36. How? Probability of E, which is 2 by 36. Sorry, probability of A, which is 2 by 36, and probability of B, which is 5 by 36. Second thing is probability of E is equal to 1 minus probability of not E. Right? So usually this is helpful when we want to calculate when it is easier to calculate probability of not E. For example, if your event E is the event where the event is not getting a double one on the throw, what is the probability? So for you, getting the probability of double one is easier, right? So you will work the other way around. You will calculate probability of not getting double one, which is 1 by 36, and you will subtract it from 1. So you will get the probability of E. Now, I think we will introduce another term here, conditional probability, and we'll cover it in the later sessions. All right. So conditional probability. What is conditional probability? The formulas that we have seen till now, they are adequate for answering the Chevalier's question, the Vermeer's question, when he was trying to evaluate the event 1 and 2, right? But now, if we already have one event which has happened, and we want to calculate the probability of another event happening over and above that, we call it conditional probability. So okay, so let's talk of this example. Okay, let's alter our experiment of throwing the double dice. Let's throw them one by one. Okay, so in first scenario, you are throwing the white dice first and then the black dice. So the scenario 1 is, what is the probability of getting the faces sum to be 3? Okay, so in scenario 1, you just simply say that it is going to be 2 by 36 because your outcomes would be uh, 2 1 1 2, right? So just 2, so 2 out of 36. Now in the scenario B, which is this one, now suppose the white die comes up 1. Okay, event C. Let's say event C is white dice shows up 1. What is the probability of A now? The probability of A, when you didn't know what was the result of first event, was 2 by 36. But now, what is it? So I leave it up to you. Think over this. We will be covering conditional probability in detail in the next session. Yeah, I think this is it. this is what I wanted to cover.